So in this video, we're going to be looking at scientific notation. And to understand scientific notation, we have to first look at base 10 in exponential expressions. Okay, so some of the reasons that you might want to know about scientific notation is numbers are really, really big in this universe, and some of them are really, really small. And so we need a way to express very large numbers and very small numbers so we can easily compare them. So for example, if we want to figure out the mass of the sun, look how many kilograms it is. Do you even know how to pronounce that number? Okay, or if we wanted to look at the width of an atom of hydrogen. Hydrogen is one of the smallest atoms that we have in terms of its mass, or is the smallest atom in terms of mass. And look at its width, okay, how many meters it is. Very teeny. Okay, and how long is a light year? So how many miles would you have to go in order for you to go the distance that light can travel in 1 year? Again, a very large number. So when you're trying to figure out things like, how far or how long would it take for us to take a trip to the nearest solar system that we feel is going to have something that's Earth-like object? We're talking about light years of travel. And so how are we going to go and build a craft that can go that distance fast enough that we can get there in one human life cycle? Okay, so scientific notation is a way that we can go ahead and accomplish writing very large numbers and very small numbers in a condensed way that allows us to easily compare. So let's look first at, base 10 and what it does. Okay, so let's say I had 10 to the first. I know that's equal to 10. And 10 squared, 10 cubed, 10 to the fourth. So I'm just multiplying by 10 repeatedly. And here's 10 to the fifth. Okay, so 10 to the fifth is 100,000, 10 to the fourth is 10,000, 10 to the third is 1,000, and 10 squared is 100, and 10 is 10. 10 to the first is 10. And 10 to the 0 is 1. So is there a relationship? Yes, there is. Let's look at the relationship that we're seeing. So if I go ahead and I look at the relationship between the exponent and the number of zeros when the exponent is positive, I see there's a direct correlation. Power of positive 1 on the base 10 gives me 1 0 after the 1. 2 zeros. If the exponent of 10 squared is 2, I get 2 zeros in 100. And 10 to the fourth resulted in 4 zeros in the number 10,000. 10 to the fifth gave me 100,000, which has 5 zeros. So if I wanted to go ahead and I wanted to expand into standard notation, a number like 10 to the eighth, I could take a 1 and write 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then kind of going in every third from the right, put in a comma that helps me pronounce it 100 million. So 10 to the eighth is the same as 100 million. 10 to the 0, I have no zeros following the 1, because we know that anything to the 0 power, if it's a real number to the 0 power, is always going to give us positive 1. Okay, so now let's go ahead and look at some negative exponents. Well, 10 to the negative 1, remember, is the reciprocal of 10 to the first. So that means this would be 1/10, and that's how we write 1/10 as a decimal. 10 squared is the reciprocal of 10, or 10 to the negative 2 is the reciprocal of 1. 10 to the negative 2 is the reciprocal of 10 squared, which means it's 1 over 100. And 10 to the negative 3 is going to be 1,000th. And 10 to the negative 4 is going to be 1/10,000th. And this is how I'm writing them as decimals. And then 10 to the negative fifth would be 1 over 100,000, which is this. Okay, so 10 to the negative 1 between the decimal point and the 1 has no zeros. And this has 1 0, 2 zeros, 3 zeros, and 4 zeros. So it doesn't match exactly what the absolute value of that exponent is when it's negative, but it has like one less zero. So another way to think, so in the number 10 to the negative 1, I get 1/10, which is 0.1. So let's look at what happened to that decimal. The number of digits after the decimal point is always going to be equal to the absolute value of the exponent. So I have 1, and this one I needed the 1 to be in the second place after the decimal point, and this one I needed it to be in the third, and this one I needed it to be in the fourth, and this one I needed to be in the fifth. Okay, so when we're writing powers of 10, a positive integer exponent means that we move the decimal point to the right corresponding number of digits, fill in with zeros. 1 followed by a number of zeros is equal to the exponent. So if my exponent is negative, I'm going to add zeros to the left of 1 in an amount equal to 1 less than the absolute value of the exponent. So kind of as a mouthful, so let's look at an example. Say we have 10 to the negative 7. Okay, well the absolute value of negative 7 is 7. So that means I'm going to add 6 zeros to the left of the 1. 1, 2, 3, 4, 5, 6. There's my decimal point, and we can put our leading 0. So this would be 1/10 millionth. Now, the reason that we can go ahead and then use those powers of 10 to help us with this thing called scientific notation is that scientific notation is a way of just moving the decimal in a number, because when we multiply by powers of 10, it just moves the decimal to the right if the exponent's positive, moves it to the left if it's negative. So scientific notation allows us to write very large or very small numbers in a condensed manner. It makes calculations for these types of numbers easier to perform. So remember in the days before calculators, having to be able to figure out things like, the distance from the Earth to the Sun, you needed to, and then go ahead and figure out how does that distance compare when we're talking about the distance from the Earth to Mars or from Mars to Venus. So they had to do calculations with these very large numbers, and they needed a more simple way to do it. And this helped a lot. So the rules for a number being written in scientific notation are that the first number, I'm going to call it the coefficient, okay, of the power of 10, has to be, and it could be positive or it can be negative, so that's why we're using absolute value symbols, bigger than 1 or exactly 1. So 1 is the absolute lowest it can go. If it was a negative number, we're talking about the highest it could go would be -1. Okay, and then this thing is we have a limit. It can't be a 2-digit number. It has to be a 1-digit number before the decimal. I can have as many decimal points as I want, but it has to be less than 10. So 9.9999999 is going to be the highest for a positive number. For a negative number, the lowest it can go is -9.999, repeating forever. The second part of scientific notation is a number with the power of 10. The exponent on it has to be an integer. So it could be negative, it could be positive, it could be 0. Has to be an integer, so you can't have an exponent that's, for example, 1.5, because that is not an integer. But you can have an exponent that's 1, you can have an exponent that's -1,000, you can have an exponent that's 888, but it has to be an integer. Okay, so we have to be able to go from writing numbers in standard notation to when we have it in scientific notation. So let's go ahead and look at an example. Okay, suppose that we have a number that is 2 5/10 times 10 to the 4th. So 10 to the 4th is really the same as 10,000. So what we're saying is that we have the 2 is going to be in the 10,000s place. So it would be 25,000. But how do I get that? Okay, so there's some easy things we can do. Every time we multiply by 10, it moves the decimal point to the right 1. Because 2.5 times 10 is 25. 25 times 10 is 100. And then I keep doing it. I've done it 1, 2, 3, 4 times, because that's what this means to do. Multiply by 10 4 times. And so if I fill in those spots between, or place values that are between where my decimal point now is and the last digit I had in my original number, which was the 5, I get 25,000. And so when the exponent is positive in scientific notation, and I'm going from scientific to standard, and so in standard notation, this would be the number 25,000. It moves the decimal point to the right, a corresponding number of digits. So let's say I have -7 and 400ths, and it's times 10 to the third. Okay, a positive exponent is going to move the decimal point to the right. It doesn't matter if the first factor is positive or negative, it's still going to do the same thing. So I'm starting without the decimal, and I know the decimal is right here. 1, 2, 3. So that means I get -7,040 is the equivalent of -7 and 400ths times 10 to the third. Okay, so what about negative exponents? So let's say I have 6 and 2/10 times 10 to the -4. Well, remember, a negative exponent divides by 10 that number of times. So in this case, 10 to the -4 means divide by 10 4 times. And every time we divide by 10, it moves the decimal point to the left 1 digit. So 1, 2, 3, 4. That's my new decimal point. 1, 2, 3 zeros in between it, and the first non-zero digit, 6. So that means that when we have a negative exponent, it's going to take the decimal point and move it to the left a corresponding number of digits. Then the extra 0 that you put in front of the decimal point does not count in that number of digits. So remember, it's always going to be from where the current decimal point is, and then the number of digits equal to the absolute value of the exponent to the left. So this would be 62 thousandths. And remember that if the base is negative, the rule still applies no matter what the exponent is in terms of being negative. So we don't do like a negative of a negative or anything. So if I had -8 and 1500ths times 10 to the -6, so then I would go ahead and take this, and I know it's going to be negative. And I'm going to move the decimal place back 6 digits. 1, 2, 3, 4, 5, 6. Decimal point goes there, and I fill in those 5 spots, okay, with zeros. And so this number would be pronounced 815 100 millionths. Negative 815 100 millionths. Now we can also take a number that's in standard notation and we can write it in scientific notation. The number 275. Okay, so the easiest way for me to go ahead and think about this is, if I want to write this in scientific notation, where do I want my decimal place to be? Well, remember, the number has to be, the smallest it can be is 1, and the biggest it can be is 9.999. So that means I need the decimal to be to the right of the 2. So that's 2 and 7500ths. Now, I know that the number got bigger, so I know it's a positive exponent. And how many digits did it move? I had to move it 2 digits. So that would be an exponent of 2. Okay, so what am I doing? I moved the decimal to the left to get it between the 2 and the 7. So that means the exponent was positive. And again, it doesn't matter if the number is positive or negative. The absolute value is what we're using for that first number. So let's say I had a number that the first significant digit is after the decimal point. Okay, so where do I want where do I want my decimal point to be? So as I go from the decimal to the right, the first non-zero digit is where I need the decimal point to be directly after. So I need it to be between the 5 and the 0 to the right of it. So I know that this number needs to be, okay, and it was a really, really small number. Very small numbers less than 1, always are going to have negative exponents. So that means it's going to be a number of negative exponents. 1, 2, 3, 4, 5, 6 decimal places. So it's negative. So I had to move my decimal point to the right to get it between the 5 and that 0 to the right of it. So when I have to move the decimal point to the right to get it where I need to be, that means it's going to have a negative exponent.